Time, and what it really is and how it really works, has always been the greatest of mysteries. But now, from the revolutionary new computational perspective of deep reality, the true nature of time finally becomes clear. To explain time, we must explain both relativistic time and our existence in a present moment through which time flows, which is the most fundamental experience of our existence. In Deep Reality Talks 1 and 2, we discovered that the universe is a computational system driven by a universal processor that's the ultimate source of time, happening, and change in the universe, and that the universe continually recomputes every coherent process with a separate application of this universal processor. Each app computes its process using the same fixed number of processor cycles. First cycles are allocated to compute any velocity in space, and then any leftover cycles are used to compute the internal evolution of the process, which is its velocity in clock time. This fixed number of processor cycles results in everything in the universe being computed with a total space plus time velocity equal to the speed of light. This is the first of the two fundamental principles that underlie relativity. So the fixed number of processor cycles used to compute every coherent process is the source of the uniform speed of light of the entire space-time fabric that can be expressed either as velocity in space or velocity in time. Now this means there are two completely different kinds of time. There's the processor cycle rate and clock time, which is computed by the processor time based on the local amount of spatial velocity present. Processor time is universal because the processor continually recomputes the entire universe in its current present moment, including all local clock time rates. So processor time continually runs at the same speed of light rate everywhere in the universe, but clock time runs at different rates throughout the universe depending on the amount of spatial velocity present. Whenever there's any spatial velocity present, clock time runs slower than the speed of light, and this is called time dilation. Now we directly experience both these kinds of time. Our experience of the present moment is our direct experience of the processor computing us and the universe, and the flow of clock time through the present moment is our experience of the processor computing our local clock time rate depending on the amount of spatial velocity we have. So our fundamental experience of the passage of time through the present moment is our direct experience of the most fundamental process of the universe, the universal processor continually recomputing our own being at the speed of light. We directly experience the most profound and fundamental process of the universe in every second of our existence. This is an enormously profound and wonderful realization, and it has all sorts of amazing implications. Realization is just a matter of understanding what we're actually experiencing. Now, as the processor continually computes the universe, it computes both the structural relationships of all particles and objects and the dimensional relationships among all particles and objects. Our brain then samples this data and displays it as a simulation of a surrounding physical space full of physical objects through which clock time flows. This works the same as a virtual reality headset that displays data stored in memory as a moving three-dimensional world. Now the universal network of all dimensional relationships forms an absolute space-time metric. It contains all the dimensional relationships among all the particles and objects in the observable universe stored in the data of the particles themselves. The important thing to understand here is that all ongoing dimensional computations are computed with respect to this universal metric. This means that all relativistic effects are computed with respect to the universal metric and become integrated with it. So whenever there is any spatial velocity with respect to this metric, there will be an actual slowing of the velocity of time to keep total space plus time velocity equal to the speed of light. And it's important to remember that spatial velocity includes the intrinsic spatial velocity objects experience within gravitational fields, which is the second fundamental principle of relativity. Now this is the view of the computational universe from the outside. It's a God's eye view of how time actually works within it. But we aren't gods that stand outside the universe looking in. We live within the universe. This means we view the absolute space-time metric from within it. And we all have some internal spatial velocity with respect to this metric, either as linear spatial velocity or because we're in the intrinsic spatial velocity of a gravitational field. This spatial velocity means our clock time will be running slower than the universal speed of light. So how does the fact we are moving within the absolute metric with slowed clock time affect our view, first, of our own time, and second, the clock times of objects moving relative to us? First, whatever spatial velocity we have inside the metric slows our own clock time rate. Our clock time is no longer running at the actual speed of light velocity of the processor, because some of the total processor cycles are being used to compute our velocity in space. Now it's extremely important to understand the difference between the processor speed of light and the actual local speed of photons of light. Light itself doesn't always travel at the speed of light relative to the absolute metric. Photons actually always travel at the velocity of local clock time, which can vary from location to location. For example, light slows to a halt trying to escape from a black hole because the enormous intrinsic spatial velocity of its gravitational field slows clock time there to a halt. So the velocity of photons within a black hole also slows to a halt as well. This is why light can't escape from black holes. So light photons always have a local velocity equal to the local clock time velocity. In the intrinsic spatial velocity of a gravitational field, they don't actually move at the universal speed of light relative to the metric. However, even in a gravitational field, every observer still observes light traveling locally at the speed of light, because both the velocity of light and the velocity of his clock time are slowed by the same amount. And the local velocity of light is measured in local clock time. This also means that every observer always experiences himself moving through clock time at the speed of light, because both his light and his clock time are slowed by the same amount. This is always true no matter how much spatial velocity he has. So an observer in the increased intrinsic spatial velocity of a gravitational field will have his local clock time slowed by the spatial velocity of the field, but will still experience local light traveling at the speed of light, and himself continually traveling forward in time at the speed of light, even though both light and his progress in time are actually slowed relative to the absolute dimensional metric. Okay, this is how an observer within the metric views his own local clock time. But how does he view the clock time of other clocks moving relative to him? Relativity calls an observer's own clock time his proper time, and the time he observes on other clocks moving relative to him, the coordinate times of those clocks. If another clock is moving relative to him, its time velocity will appear to be slowed so that its total space plus time velocity still equals the speed of light. Now the slowing an observer sees depends on the apparent spatial velocity of the clock relative to him. The moving clock will be observed running slower depending on its spatial velocity relative to the observer. This means different observers could observe the same clock running at different rates depending on its different amount of spatial velocity relative to them. So if two clocks are moving relative to each other, they each see the other clock moving with the same spatial velocity in the opposite direction. So each clock sees the other running slower. In this way, both see the total space plus time velocity of the other clock equal to the speed of light. Now obviously both observers can be right, because clocks can't actually run at two different rates at the same time. This means that time dilation due only to relative spatial velocity among observers isn't an actual relativistic effect, but only an observational relativistic effect. It vanishes with no trace as soon as the relative motion stops. So actual relativistic effects are due to spatial velocity relative to the computational metric, because they're computed with respect to it, but observational effects are due to spatial velocity relative to an observer. The difference is that actual relativistic effects are permanent and agreed to by all informed observers, whereas observational relativistic effects vanish as soon as the relative spatial velocity stops without any lasting effects. So actual relativistic effects are with respect to the absolute dimensional metric, but the often contradictory observational effects are due simply to relative spatial velocity with respect to an observer. So recalling that relative spatial velocity includes both linear spatial velocity and any difference in the intrinsic spatial velocity of a gravitational field, this explains all aspects of how clock time appears to observers in all cases. Now, the distinction between actual and observable relativistic effects is crucial because only the existence of an absolute dimensional metric enables us to accurately explain both the actual time dilation of the space-traveling twin and to solve the mystery of rotation. The existence of an absolute computational space-time metric is a little understood aspect of relativity that not only solves the problem of why some spatial velocity produces actual permanent effects and some only temporary observational effects, but also solves the problem of what rotation is actually relative to, a problem that's been unsolved ever since Isaac Newton posed it centuries ago. Actual rotation is absolute in the sense that it self-manifests by the presence of centrifugal force and the resistance to tilting of the axis of rotation, which is why gyroscopes work. But the question is, what is rotation actually relative to that makes it behave this way? We might think rotation is relative to the surface of the Earth, but this can't be true, because the Earth's surface curves and the gyroscope maintains its same orientation no matter where or how it's moved. Over 100 years ago, Max Planck suggested rotation was with respect to the aggregate mass of the universe, but there's no known principle of science or relativity that explains why this should be true, so it's remained a mystery. Turns out that Planck was correct, but only deep reality shows why. He's correct because the dimensionality of rotation, like everything in the universe, is computed with respect to the absolute dimensional metric, which is the metric of all particles in the universe, and thus all the mass in the universe. So rotation turns out to be another example of an actual as opposed to an observational relativistic effect. So by measuring both what specific spatial velocities result in how much actual time dilation and exactly what orientation rotation is relative to, we can discern the actual form of the absolute dimensional metric around us, which would otherwise be invisible. Rotation and actual time dilation are how the absolute dimensional metric reveals itself to us. Now, it's important to note the little-known fact that relativity itself confirms the existence of a present moment and also explains the arrow of time. So relativity itself actually requires the existence of a present moment and an arrow of time. The fundamental principle of relativity is that everything in the universe is computed with a total space plus time velocity equal to the speed of light. This means that everything in the universe continually travels through combined space and time at the speed of light. Nothing is static. This means that everything must be at one and only one position in both space and time at any moment. And the one position anything is in time is clearly its present moment. This is how relativity itself proves the existence of a present moment. Now, the current present moment of every individual thing in the universe is the same universal present moment of everything in the universe. It's the single current universal present moment in which the entire universe exists. This is easy to understand because in every successive current present moment of time, everything else anywhere in the universe must always be doing something. Thus, there must be a common current universal present moment in which everything exists at the same time. And in addition, the familiar space-traveling twin example also proves a universal present moment, because the twins always part in a shared present moment and always meet again in another shared present moment. This is true even though their clock times ran at different rates during their separation. This conclusively demonstrates that all observers share a common universal present moment through which their individual clock times can flow at different rates. Now, the arrow of time has long been a fundamental mystery. Why does time flow in one and only one direction? Deep reality reveals the simple solution. Because the single universal processor continually computes the entire universe with cycles running in the same direction, all the local clock times it computes also flow in that same direction. This is the source of the arrow of time. We experience this as the arrow of our own local clock time flowing through the present moment. Now, some believe the arrow of time is due to increasing entropy, but this is clearly false because entropy varies widely throughout the universe with no connection whatsoever to how local clock time varies. Also, entropy isn't even fundamental because it depends entirely on the distribution of forces in the universe, which can change. For example, in an initially static universe, the ultimate entropy state would be a single universal black hole. But in a universe with an ever-accelerating Hubble expansion, the ultimate entropy state is a vast, nearly empty universe, just the opposite. So the arrow of time has nothing to do with entropy. Its source is the fundamental principle that everything in the universe is continually moving at the speed of light through space-time, the same fundamental principle that underlies relativity and the present moment as well. Additional proofs and discussions are given in my books. Now, the computational concept of two kinds of time has many important implications. For one thing, it reveals that the overall geometry of the universe is a four-dimensional hypersphere. Our three dimensions of space are the surface in the current present moment, and the radial dimension is the processor time extending back to the Big Bang at the center. It's important to understand that the entire universe is only the three-dimensional surface of the hypersphere in the current present moment. The past radial dimension and spatial surfaces no longer exist. All that exists is the current entire universe in the current universal present moment. Our entire observable universe is just the three-dimensional surface of the four-dimensional hypersphere. Thus, the universe is four-dimensional, but its time dimension contains only a single actual point, the point of current processor time. The continual ticking of the processor continually recomputes the entire surface in the single point of the next current present moment. And as it's recomputed, every point within the surface is computed with a total space plus clock time velocity equal to the speed of light. This produces all the different local clock time rates of all the different processes within the surface. But all these local clock time rates exist only in the current present moment surface and have nothing to do with the continual uniform extension of the radius, which is due to the fixed processor rate of present moment time. So each set of processor cycles creates one tick of present moment time as it computes the entire next surface of the hypersphere. So the surface continually expands from one layer to the next due to the progressive passage of processor time extending the radius. Now note that the radius extends uniformly in processor time, but the spatial surface has expanded at different rates throughout its history, most notably during the inflationary period right up to the Big Bang. So how can a uniform lengthening of the radius produce different rates of expansion on the surface? The key is to understand that the extension of the radius is due to ticks of processor time, but the expansion rates of the surface are measured in clock time. And since processor time can compute different clock times, this isn't inconsistent. How this actually works will be explained in the upcoming talk, Deep Reality Talk on Cosmology. And again, we directly experience this fundamental recomputation and expansion of the hypersphere in our own being, in our own experience of a present moment through which clock time flows. Now, amazingly, we can also directly confirm the four-dimensional hyperspherical geometry of the universe with our own two eyes. We actually see it opened up before us. We actually see down the radial past-time dimension of the hypersphere in all directions from every point in its three-dimensional surface. The further we look, the further back in time we see. So with powerful enough telescopes, we can actually see back over 13 billion years down the past radial dimension of the hypersphere to when our universe was still young. This is exactly what a hypersphere looks like from the inside. So when we look out in any direction, the universal hypersphere is revealed before us. Of course, the past universe we see back then no longer exists. We see what it looked like back then just because light from there is now reaching us. What's actually going on now at those distances is unseen and unknowable. In actuality, all those most distant parts of the universe now exist in the exact same present moment we are experiencing right now. There's just no way for us to see what's actually happening there because it will take light currently billions of years to reach us. And finally, this new understanding of how time really works reveals the actual truth about time travel and debunks supposed paradoxes like going back in time and killing your mom before you were born, or for that matter, the impossibility of changing the past at all or ever visiting it. Since the entire universe exists entirely within the current universal present moment, in which the universal processor is recomputing it, there's just no past to travel back to or change. Time travel to the past is simply impossible, because the past just doesn't exist. So sadly, no going back to view dinosaurs or improving the present by changing the past. But we are all time travelers. We all continually travel forward in time at the rate of our local clock time is being computed, which is the local speed of light. The passage of clock time is us traveling forward in time at the local speed of light. So we all do continually travel forward in time. But as we all continually travel forward in time at our local clock time rates, we continually remain in the universal present moment as it's recomputed tick by tick across the entire universe. We continually remain in the present even as we travel forward in clock time, because the current present moment is all that exists and clock times are computed within it. So there's no traveling to another present because no other present actually exists than the one we're currently in. The entire universe exists only within the current present moment, so there's simply no other place to go. It's simply impossible to ever leave the present because it's all that exists. All that currently exists is the entire universe in the current universal present moment. Outside this, there's not even nothing. So it's completely impossible to travel to any actual past or future because there are no actual pasts or futures. They simply don't exist. However, we can travel through clock time at different rates within the present moment, depending on our spatial velocity. This means we can age slower or faster as the present moment progresses, depending on our spatial velocity. So time travel is possible in this limited sense if it's properly understood. For example, a time traveler could theoretically take off from ancient Rome 2,000 years ago and travel at a high velocity through space to slow his aging and return to Earth today not too much older than when he left. So an ancient Roman could land his spaceship today and give us an eyewitness account of life back in ancient Rome, or from any time or place in the past for that matter. And he could show us his photos and videos from there as well. Only in this sense is time travel possible. Colloquially, some might say he traveled to the future, but actually he just traveled through the present much more slowly for 2,000 years until he landed back on Earth. So also with the right spaceship, we could depart Earth today, travel at high velocity through space, and arrange to return at any time in the future we wished. But again, we aren't actually traveling to the future in this scenario. We're simply remaining in the present moment and a much slower clock for much, much longer. Because time passes so slowly on our spaceship, we could live long enough to return to Earth many years or centuries since. So when we understand the truth about time travel, we immediately see there are no possible paradoxes where someone could go back in time and kill his mom before he was born. This is simply not possible because there's no actual past to return to. Once computed, the past is forever fixed and unalterable. Deep reality makes the universe consistent again. So our new understanding of time also reveals how long-distance space travel is theoretically possible within a single human lifetime. The faster a spaceship travels in space, the slower it travels in time. So if we travel fast enough through space, approaching the speed of light, our velocity in time can slow to almost nothing, and we would hardly age at all. For example, to travel the 25,000 light years from Earth to the center of the galaxy, assuming a constant 1g acceleration and deceleration, the same as Earth's gravity, would take only 19 plus years by clocks on the spaceship, even though it would take a little over 25,000 years on clocks back here on Earth. So even a round trip to the center of the galaxy could easily be made within a single human lifetime by the clocks of the travelers. So traveling vast distances in space in very little time is certainly theoretically possible. However, the necessary propulsion system and the near impossibility of avoiding collisions with interstellar objects at near light speed makes it questionable. Okay, so this wraps up the deep reality talk on time, what it really is and how it really works. We've covered the two kinds of time, present moment time and the clock time it computes, how clock time behaves under various relativistic conditions, and revealed its implications for time and space travel and the geometry of the universe. All this is covered in much greater detail in my book, Universal Reality 2.0. But there are many more amazing insights to come in the next deep reality talk on cosmology, including a completely new understanding of black holes, dark matter, dark energy, and why we may be living in a big bounce universe. So stay tuned and subscribe to stay informed.